Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 106 in our incredible new tutorial series where you are unleashing the power of your Raspberry Pi Pico W. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Kepler kit for Raspberry Pi Pico W. Now, hopefully most of you guys already have your kit, but if you don't, take a look down in the description. There is a link over to Amazon and you can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot easier if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what I'm going to do is I'm going to teach you about echolocation. What is echolocation? Well, let's take inspiration from the animal kingdom and let's look at our friend the bat. 1,000 bats can be flying in a flock in a completely dark cave, and they can navigate it without running into each other and without running into a wall. And again, I say in the dark. How do they do that? Well, each bat emits its own unique little chirp. It chirps, that chirp goes out and runs into whatever is in front of it and then comes back, and the bat hears the chirp. By how quickly the chirp returns, that gives the bat knowledge of how far in front of him the obstruction is, and then the distortions in the chirp let him know, is it a wall or is it something small like another bat? And so it's really absolutely amazing. Whales underwater also navigate using echolocation, a similar principle. They put out a big kind of groan and then wait to hear the groan come back. And then in the physical world, submarines, it's very dark at the bottom of the ocean, and they do not navigate optically. They navigate based on sonar. They give out a little ping and then they wait to hear the ping back, and then from that they can discern where the obstacles are around them. And so that's kind of the quick synopsis of echolocation. And we're going to do our first echolocation project today. Yes, we are. So you will need to get into your most excellent kit, and you will need to find your HC-SR-04 ultrasonic sensor. And what we're going to do today is we're going to use this little sensor. We're going to hook it up. We're going to program it up, and then we are going to send little pings. We're going to wait for the ping to return, and then based on that, we're going to calculate the distance between the sensor and the target. Sound good? I hope it does. Well, let's kind of get the mundane things out of the way. Let me see if I can get the mundane things out of the way first. And what we are going to do is we are going to come over here. And let's see, I think this is the view that we're going to want, and we are going to want to get me out of your way. And then I'm going to get a little further out of your way just to make sure that you can see this, okay? So what we're doing is we are connecting. There is 1, 2, 3, 4 pins going left to right. 1, 2, 3, 4 pins going left to right. The leftmost pin goes to 3.3 volts. Okay, how do we get to 3.3 volts? We come down here to the power rail, and then we come over here to physical pin. What is that? Are they counted that way? It's the 5th one over down there, and that is physical pin 36. So this is pin 40, and then this is pin, let's see, this is pin 40, 39, 38, 37, and then 36. So physical pin 36 is creating the power rail, and then physical pin 38 here is creating the ground rail. Then over here, the leftmost pin, it goes down to the power rail, 3.3 volts. The next pin we call the trigger pin, and the trigger pin comes over to, let me look and make sure that I say it right. The trigger pin comes over to pin 16. GPIO pin 16, and then the next pin over, the third pin over, is the echo pin, and the echo pin goes over to GPIO pin 17. So trigger 16, echo is 17, and then the fourth pin is the ground, and we bring it down to the ground rail. Okay, so that is about as easy as you can get as far as a hookup. But now, how does this thing work? Okay, this is the way this thing works. All right, so let me come over here and let's draw our sensor. So, okay, so what I'm going to do is I'm going to draw our sensor, and you know it's got these two cylinders coming out. And then it's got like a little clock here, I think. And then we're going to come over here, and what we're going to have is we are going to have a target, okay? And then there is some distance. I should draw that better. I think really what I find works best is measuring the distance from about the front of these cylinders. And so this is how we measure distance from the sensor to the target. Okay, so that's easy enough. So how does this thing work? Okay, how does this thing work? Let me see if I can get a color here. All right, so how does this thing work? Well, you've got the trigger pin, and what you want to do is on your trigger pin, you want to generate a 10 microsecond pulse. So this is the trigger pin. So I will call that trig. And then what you want to generate here is 10 microseconds, like that. Okay, now what happens when you put that 10 microsecond pulse on your trigger pin? Well, the sensor is going to see the trigger pin, and then it is going to wait for some period of time, maybe a few milliseconds, and then what it is going to do is it is going to launch the ping. So it is going to launch the ping. And as soon as it launches the ping, it sends the echo pin high. So this is the echo pin, and it goes high. It goes high right at the instant that the ping is launched. Now, once it launches the ping, it sits and listens. So this is going to be listening as the ping travels to the target, and then it bounces off the target. Of course, it's not going like a laser beam, it's spreading out, but it's easier to draw it like this, okay? And it comes back, and then right here, it is detected, okay? It is detected. We hit the ping that we send, we hear the ping come back. Well, as the ping is traveling, the echo pin stays high. As the ping is traveling, the echo pin stays high. But once it hears the echo return, then the echo pin goes low. Now, what is this? Okay, what is this? This is the ping time, okay? That is the amount of time that our ping is in flight. It's a time, and the time is in microseconds. And that is millionths of a second. Microseconds, one millionth of a second. There's a million microseconds in a second. Now, what do we want to know? What is it that we want to know? We want to know the distance. We want to know the distance. Well, how do we get the distance? What do we know about distance? Distance is equal to rate times time. That's like if I'm going 60 miles an hour for 2 hours, I go 120 miles. 60 miles per hour times 2 hours would be 120 miles. What is that? That's rate times time. So what is t? T is our ping time in microseconds. Okay. What is our rate? Well, it's how fast the ping is going. How fast is the ping going? It is a sound. It is going the speed of sound. Now, I want to, and I'll show you in a minute why I want to do that. Well, I guess I can just show you right now real quick. I have this little nice pad on my desktop, and it is marked off in centimeters. And so to check our accuracy, it's really easiest for me to have this thing measure in centimeters. You can measure in inches, you can measure in yards, you can measure in yards, but you've just got to do the math for the units that you're going to use. For me, what am I going to measure? I am going to measure in centimeters. Now, what do I know about the speed of sound? Well, I can't just go up and look at it in any old units, but what I can get is in kilometers per hour, okay? And the speed of sound is 1,234.8 kilometers km per hour, all right? Now, what is the problem? I don't want kilometers per hour. I want what? Centimeters per microsecond. So what do I have to do? I have to do dimensional analysis. Dimensional analysis is where you have you're in the units that you're in, and that there's the units that you want. And how do you go from here to here? By a series of multiplying by 1. I'm going to multiply by 1, multiply by 1, multiply by 1, multiply by 1. But as I multiply by 1, I'm going to keep track of my units. So what is the problem? The problem is I am in kilometers and I want to be in centimeters. Well, what do I know? I'm going to multiply by 1, which means the numerator and the denominator needs to be the same. Now, what do I want to get rid of? I don't want to be in kilometers, so I want to get rid of kilometers. So I put kilometers in the denominator. But what do I know? I know 1 kilometer is 1,000 meters. So if I multiply 1,000 meters over 1 kilometer, 1,000 meters is the same as 1 kilometer. I haven't changed anything. And look what happens. This km and this km make 1. And now what do I have? I would have the speed of sound in meters per hour. Do I want to be in meters per hour? No, I don't, but I've gotten closer than I was before. Now, what is it that I don't want? I don't want meters. I want to get rid of meters, so I'm going to put that in the denominator. But what do I know? 1 meter is equal to 100 centimeters. Okay? Is that good? Now, look what happens. I have meters over meters. That makes 1. And now what units am I in? Centimeters per hour. Why am I happy? I'm in the right length. Now I've got to get in the right time. So you guys do it with me. Now, do I want hour in the denominator? No, I don't. I want microseconds, but I'm not going to go in one jump. If I want to get rid of hour, it's in the denominator, so I need to put hour in the numerator. So 1 hour is equal to 3,600 seconds. Okay, now look what happened. Look what happened. Hour, because hour is in the numerator and the denominator, hour over hour makes 1. Now what unit am I in? Centimeters per second. Stay with me, guys. We are almost there. Do I want to be in seconds? No, I want to be in microseconds. What do I want to get rid of? Seconds. It's in the denominator. So here I want to put it in the numerator. 1 second is equal to 1,000,000 microseconds. Look at the magic now. Seconds over seconds make 1. And what am I in? Centimeters per microsecond. What do I have to do now? I just have to come in and look at this. I'm going to kind of step you through it, and you do this on the calculator. You take 1234.8, and then you multiply it by 1,000. That's in the numerator. You multiply it by 100. That's in the numerator. Then you take that and divide by 3,600, and then take that and divide by 1,000,000. And what do you get? You get 0.0343, and we're in units of what? Centimeters per microsecond. Okay, now all I have to do is measure. Now what do I know? I know distance in centimeters. I know distance in centimeters is going to be rate, which is 0.0343 times the time. How do I get the time? I measure it with the HC-SR-04. Okay, so then I can calculate the distance to a target. Okay, does that make sense? That should be pretty good. Okay, that should be pretty good. So let's get over here, and I think we're ready to start coding this thing up. Did you guys get yours? Did you guys get yours hooked up? I got to do a little bit of desktop management here as I go from the sketch pad over to the keyboard. Okay, so let's see if we can come over here and let's see if we start coding. Now guys, this is what I got to tell you. We are now on lesson number 106. So we are not at this point going to be going in and loading libraries and programming like little children. We now have the skills. We have the skills that we need in order to go in and kind of really start working with these devices more at the raw code level, if that makes sense. Okay, and so let's see. I'm almost there. Okay, I think I can come over here now. All right, so now what are we going to do? We are going to we're going to use those GPIO pins. So we're going to import machine like that, and then we're going to import time, and then I'm going to have a trig underscore pin. Okay, and that trig pin we said was 16, pin 16, and then I have an echo underscore pin and that was pin 17. I'll get my typing going here in a minute. Got to get those fingers warmed up, right? Okay, now what do? I'm going to say trig is going to be equal to machine dot pin of what? Echo pin, or trig pin. Yeah. Trig pin like that, and then that needs to be a machine dot pin dot out like that. Okay, and then echo is going to be equal to, our echo object is going to be machine dot pin, and what is this going to be? This is going to be echo pin, and that needs to be machine dot pin dot out like that. Okay, does that make sense? I think that makes sense. All right, so we have a trig pin and we have an echo pin that are set up. Now, what did I say the first thing that we wanted to do? Okay, I'm just going to create a little function that does this. No, I'll create a little function that does this. So I'm going to define a function called distance that will allow us to find the distance. We've done functions before. What am I going to do? I'm going to set trig low, and that's going to take the trig pin low. I'm going to create that 10 microsecond pulse. Now I am going to time.sleep underscore US for microseconds. And how long? 2 microseconds. We're going to give that a little time to be in its rest position. Now I'm going to take, doesn't count as a mistake if you catch it before you run it. Then I'm going to take trig, high, like that. Okay. Now I'm going to time.sleep underscore US for microseconds. How long did we say that trigger pulse needed to be? 10 microseconds. Okay. 10 microseconds. And then what do? We're going to go trig dot low. Trig low. Now, what do I want to do? I want to wait for trig to go up. Okay, so while, and also I need to measure what time it is right now, because then I will have that. No, I don't want to do that yet. What I want to do is I want to wait for a 1. So I'm going to say while echo dot value, while echo value equals 0. Now what is that echo value equals 0? That is, I'm going to sit here and I'm going to pause right between the trigger. When I put that trigger signal down, I'm going to pause there until I see the echo pin go up. Okay, I'm going to pause there until I see the echo pin go up. So while echo value equals 0, all right, what am I going to do? I'm going to do absolutely nothing. I'm going to pass. Okay, but now if it drops out of that loop, that means I've got a 1. That means that the ping has been launched. So I need to know what time was the ping launched. So I'm going to say time 2 is equal to time.ticks in microseconds. So that just gets kind of the present clock time in microseconds. So let me look at that very carefully. Time.ticks microseconds. That is going to be time 1. That's the first time. That's when it goes up. That's when it goes up. Okay. Time 1. All right. Now, while echo dot value equal 1. So now this while loop is going to wait as long as that pulse is up. And what's it going to do? It's going to do absolutely nothing but wait. So what am I going to do? I'm going to pass. So it's going to just sit there and loop as long as that echo pin is high. And then as soon as the echo pin comes low, I'm going to drop out of that, and then I'll get my time 2 is equal to time.ticks underscore microseconds, like that. And so now I have a time 1 and I have a time 2. Okay, I've got a time 1 and I have a time 2. Now, what do I want to do? Well, this is supposed to find the distance, right? This is supposed to find the distance. So then what I'm going to do is I'm just going to say that ping time is equal to time dot. I mean, what you could easily do is say time 2 minus time 1. And that would be the ping time. But there's a little thing that you should learn, because sometimes this clock rolls over when it gets to a really big integer. And if you happen to be unlucky and make your measurement, your first measurement before it rolls over and your second one after, then you would get strange results. And so it will compensate for that if you say time dot ticks underscore difference of time 2 time 1. Okay, this is exactly the same thing as time 2 minus time 1, but if you happen to be that 1 in a billion chance that you did your measurement right when the clock rolls over, it will compensate and fix it if you do things this way. So this is just kind of an important thing to know. It's a nice little thing to know. Now, what can I do? I can say that my distance is equal to the rate, which was 0.0343 times the time. What was the time? Ping time, like that. Now what do? I return D for distance. Okay? Now, what will I do down in my while loop? While true, when it's true, true is always true. We created an infinite loop, and now I can say my distance is equal to distance, which we just defined up here, and then I will say print distance to target space there, and then I'm going to print dist, and then I'm going to print space centimeters, like that. And now let's do a delay. Let's do a time dot sleep of, let's do 250 milliseconds, like that. I might need to do milliseconds. I can't remember, like the delay in Arduino is milliseconds and the delay in MicroPython is seconds, I think. So it's easy to get confused if you're not careful. But if I say _ms, I'm sure it will give me milliseconds. Okay, let's come over here and let's see if we can set this thing up where you can see it. I'll have to do a little management here. Okay. Let's see if I can back off this a little bit. Okay, so now I'm going to put the target right here. Okay, and then I'm going to put the target right there. And guys, let me show you something you got to be careful of. You've got to aim straight, right? Because if I aim like this, what distance is it going to measure from here to here? Or if I have it like this, it's going to measure from here to here. So when you're testing this thing, you got to keep things square. And then I'm also going to kind of try to shoot it down this line. So you see how I'm lining this up with my grid. And then over here, I'm lining this up with my grid. And let's come over here and let's go to 10 centimeters, just like that. And what is really cool here, ooh, after I had it aligned so perfectly, that one hurt, my friends, that one hurt. So I'm going to line it up, okay, and then I'm going to come over here to 10. I'm going to line it up so you can see I'm 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the front. I'm 10 to the front of those cylinders. I could sit here all day just trying to get that perfectly aligned and perfectly in the middle. Okay, so that looks good. So now what I'm going to do is I'm going to come over here and I'm going to run it. So what I'll do is I will I will come over here and we'll run it. We might even have some errors in there. I don't know. Yeah, we got an error. SIM isn't defined. What is that nonsense in line 12? What is that? Time. Time. We will go ahead and use the preferred spelling of time. Okay. And then pin object has no attribute. High. And what did I do there? Ah, that's a little one. Okay. Little case problem there. Okay, man, I was just doing terrible, wasn't I? Line 26, print distance. Dist is equal to distance. Now that one's got me. Oh, sleep microseconds. Okay, again. I'm being very sloppy on my uppercase, lowercase. Hopefully you guys caught most of this. All right. Okay, now it's running. Okay, trigger pin. Let's make sure I did trigger pin and echo pin right. Yeah, that looks right. So I'm not getting anything back. I'm not getting anything back. Okay, and it's not running, and let's see. Okay, so probably since it's not printing anything at all, it's probably getting caught in this while loop. In this first while loop, it is just getting stuck there. It never comes out, and it would never come out if it never sees the pulse going up. And it would never see the pulse going up if you had defined echo pin incorrectly, that the echo pin is an N pin because I'm reading from it. Okay, now let's take a look back over here. Let's make sure we got everything lined up, and let's put this again right at the 10 centimeter mark, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We will come back over here to this view, I think would be a good one. And now let's go ahead and run this thing. And we are getting, boom, we're getting readings. And what are we reading? We are reading 22, or we're reading about 20 or 21 centimeters. Boom. Now, what is the problem? The problem is it's not very accurate, because it is really more like what? More like exactly 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so why am I getting an answer that is off by a factor of 2? Well, let's try 5 centimeters. So we will come into 5 centimeters, and now we are reading 10, right? So when we come into 5, now we are reading 10. So I ask you, where was our mistake? Was it a math mistake? Was it we didn't write down the speed of sound right? Was it that we didn't measure things right? Or is it that we have to think about our friend the ping? Okay, now let's imagine that we are the ping. If we start here and we come here and then we come back, what have we done? The ping has traversed D twice, once to get there, once to get back. So Mr. Ping Time is telling me his travel time there and back. But we don't want to know the distance the ping traveled. We want to know the distance to the target. And so in that case, we would need to do what? We would need to take that ping time, and we would need to up here that ping time, and we would need to divide by 2. And that way we're just taking the distance to the target, not to the target and back. Okay, so let's go ahead and run this thing again. And now we are getting, at 5, we are getting a much more appealing 5 centimeters. And then if we come out to 10, we are reading 10 or 11. That is pretty darn accurate, between 10 and 11. And then if we come out to 15, we are measuring 15.5. And then if we come out to 20, we are measuring 20. Boom, math works, engineering works. Is that not great? Okay, so all of this is very good, but now what I'm going to do is I am going to stop this program, and now if you remember over here, what I want to see is how does this look on the scope? And part of what I'm going to do here is show you the importance of having a scope. If you can afford one, it's important to have a scope. And we're going to learn kind of two things in this lesson besides echolocation, okay? Two things we're going to learn besides echolocation. And let's see. All right, so now what I am going to do is I am going to come over to this most excellent view. And then what you can see is you can see that I have a scope set up. And I've got that scope set up where I am, what, 5, 10, 15 centimeters. I'm 15 centimeters from the target. And then I have a probe on my trigger pin, and I have a probe on my echo pin. Now, if we come back over here, what is it that this component says that it needs for the trigger pulse? For the that was crazy. What does it need for the trigger pulse? It needs 10 microseconds. And we generated a 10 microsecond pulse, right? So everything should be very good. So we're going to come here, and now I am going to run the program. And then what you see here is you can see this is my echo pulse, and it's kind of jumping around a little bit. It's not really completely stable. And remember how we saw our measurement numbers kind of jumping around a little bit as well. And then over here in yellow, this is the trigger pulse. But remember, the trigger pulse was 10 microseconds, so it was very hard to see. So I need to come over here and I need to adjust my time scale. And I'm expanding this out and scooting it over so we can look at this trigger pulse. This is set on 20 microseconds per division. And I'm at what? 1 microsecond. And it's between 1 microsecond and 2. I mean, it's between 1 division and 2 divisions. As this thing is jumping around, it's jumping between 1 division and 2 divisions, and that's at 20 microseconds per division. So what trigger pulse am I actually generating? Between 20 microseconds and 40 microseconds. Why? Because MicroPython is lousy at timing. It's absolutely lousy at timing. And you can see over here, we did it perfectly. We said go high and then wait 10 microseconds and go low. But it stayed high between 20 and 40 microseconds, okay? And if we come back over here, not that view, I think it's this view, and then let's shut this down back to where we can see our pulse. Okay, if you sit and watch this pulse, it's moving around, leading to errors in our measurement. Because why? We cannot trust MicroPython and the Raspberry Pi Pico W to do timing accurately. Now, right now when we're sitting here, it's kind of looking okay, but our code is really simple, not doing anything else. As our code becomes more complicated, all of a sudden MicroPython, while it's supposed to be timing our pulse perfectly, it goes out and does random strange things, and you can never depend on the trigger pulse that you're generating, and you can never depend on that timing of how you are timing the duration of that up pulse. And so we would be setting ourselves up for disaster if we were using this in a real application, because we never know exactly what MicroPython is going to do related to what? Timing. All right. Now, you guys that have stuck with us for 106 lessons now, there should be a light bulb going off in your head. What do we have here? A timing problem. What is the ultimate solution to precise timing? It is the what? It is the state machines. So I've shown you a way to do it poorly here. I've shown you a way to do it poorly as a demonstration. But if you were really going to be doing this, how would you want to do it? You would want to do it with the state machines. So we've kind of learned two very important things here today. Well, we've learned about echolocation, but one very important thing that we learned is we got another example of dimensional analysis. And I would say as an engineer, probably the three most important things that you need to know in engineering. One is dimensional analysis, because you can work in any units that you want if you understand how to use dimensional analysis. You want to be an engineer, master dimensional analysis. The second thing is master linear equations. How much of the last 106 lessons have we needed to create the equation of a line? Probably about half the lesson. So linear equations are important. Dimensional analysis is important. And the third thing is calculus, differentiating and integrating. I wish I could teach you calculus on this channel. Maybe one day I will do that. But those are three really important things. And then the fourth thing we learned is you cannot trust the timing on a Raspberry Pi Pico. And so you can see the importance of having a oscilloscope. If you can't afford oscilloscope, I understand you can continue to fully benefit from these lessons without an oscilloscope. But if you have a few coins lying around, I think that you can see why the oscilloscope is important, because without this oscilloscope, we would have no way of knowing that we weren't getting an accurate pulse and we weren't getting a uniform pulse. But when we have this oscilloscope, it helps us to debug. I do have a link to the oscilloscope I use down in the description. If you guys have a few coins, it would be a great thing to add to your bench top. But it is time for us to talk about homework. Can you guys guess what your homework is? I've shown you the easy beginner way to work with the ultrasonic sensor. But what you need to do is you need to go out and you need to make it work with the state machine. So what are you going to do with the state machine? Well, the state machine needs to create. The state machine needs to create those pulses. It needs to precisely create the trigger pulse, and then it needs to precisely observe and count the number of clock cycles that high pulse is on your echo pin. Now, you can't turn that into 25 microseconds, but you could return the number 25, and you would know that that number 25 is in microseconds. So I give you a hint. You've got to count every single clock cycle in your loop, and you have to take that into consideration when you then determine what your pulse width is. So that's your homework. Make this thing work right using the state machines. Guys, I hope you are enjoying taking this class as much as I am making it. It's at this point that every week I give a big shout out to my Patreon supporters. These lessons that get into this depth of programming where we're doing precise timing with state machines and stuff, these don't get millions or hundreds of thousands of views. They get 1,000 or 2,000 or 3,000 of people who are really, really serious about learning and not just copying and pasting. So that's good. People learn. But the bad thing is the only way that I can do this type of lesson is with the support from my Patreon. So I thank you guys. You can also help this channel by giving the video a thumbs up and leaving a comment down below. If you haven't already, make sure you subscribe to the channel, and when you do, ring that bell so you'll get notifications when future lessons drop. And most importantly, share this video with other people, because the world needs more people doing engineering and fewer people sitting around watching silly cat videos. Paul McWhorter, TopTechBoy.com. I will talk to you guys later.